So chapter 19 is electrochemistry, which is building off of the redox reactions that we learned about back in chapter 4. So brief recap of what redox reactions are. So when I say redox, these are coupled reactions. Coupled, part of it's a reduction, part of it is an oxidation. Yes? You can log it. I don't know. I haven't tried it today. So the reduction part of it is the gaining of electrons. So gaining electrons is reduction, which sounds kind of confusing. Why are you being reduced if you're gaining something? But even though you're gaining electrons, what is going down as you gain electrons? The charge. Or if you're not a charged particle, at least your oxidation number is being reduced. That's why it's called reduction. While losing electrons is the oxidation. So we had a couple of different ways of remembering this. There was the famous Leo the lion says grr, losing electrons is oxidation, gaining electrons is reduction. In the video we watched last time, there was oil rig. Oxidation is losing, and reduction is gaining. So whichever way you need to remember them. We also in chapter 4 balanced redox reactions. The easiest way about going about this was when we were just dealing with metals and just looking at their net ionic reaction, meaning we were ignoring any spectator ions. So for example, let's see here. Let me pull an example from chapter 4. See if we can remember how exactly we balance this thing. See here. Aluminum solid plus iron 2 plus aqueous goes to aluminum 3 plus aqueous and solid iron. So by the rules of chapter 3 in stoichiometry and conservation of mass and all that good stuff, it's technically balanced. I start with 1 aluminum, I end with 1 aluminum. I start with 1 iron, I end with 1 iron. But it is not balanced as far as the number of electrons involved. So in redox reactions, when we balance them, we balance the number of electrons. And there were 3 steps to balance a simple redox reaction. Break them into the 2 half reactions, meaning show the half that was a reduction, show the half that was an oxidation, and how many electrons were involved. Balance, so those number of electrons are the same, and then step 3, add them back together. So first of all, just looking at this, if gaining electrons is reduction, meaning your charge is going to go down, which one was reduced, aluminum or iron 2 plus? Iron 2 plus, because iron 2 plus went from a charge here, darker color, 2 plus down to a charge of, it's not shown, but it's understood 0. That charge went down by doing what? What did iron do to do that? How? What? Gaining. How many electrons would have to gain to go from 2 plus down to 0? 2 electrons. So if we were to write the reduction half reaction, doesn't matter which one you write first, oxidation or reduction, so let's write the reduction first. So the reduction half reaction would look like this. Reduction half reaction would be iron 2 plus gains 2 electrons. Now, you know what, we're just going to ignore the states of matter for now. We'll put them back in at the end. Gains 2 electrons, so plus 2 electrons. Man, that is bad today. and becomes iron with no charge. So that is your reduction half reaction. So if iron got reduced, what got oxidized? Aluminum. Aluminum went from 0 charge to 3+ charge. We learned way back in chapter 2 that you gain a positive charge by losing electrons. In this case, how many electrons would aluminum have to lose? 3. So the oxidation half reaction would show starting with aluminum, and you end up being aluminum 3+, and it lost 3 electrons, so those 3 electrons are going to be shown as coming out on the product end there. So that was step 1, write the 2 half reactions. Step 2 is balancing the electrons. Are these electrons already balanced as written? What do I mean by that? When I have a reduction, it's gaining electrons. Where are those electrons coming from? There's not just free electrons floating around out there. Where are the electrons coming from? Iron gained electrons. Who gave him the electrons? Aluminum. So oxidation reduction reactions are technically a transfer of electrons. So if they're a transfer of electrons, one thing is giving them to the other thing. That means they must be the same number of electrons shown in both half reactions, because those are the electrons that are transferred. If aluminum gave up 3 electrons, but iron only gained 2, then they're not balanced. So what could we multiply this first reaction by and the second reaction by to get them balanced? 3 and 2, good. Because 2 electrons and 3 electrons, least common multiple of that is 6. So I multiply the first equation by 3 and the second equation by 2. Go ahead and rewrite them, distributing the 3 and the 2. That's the second step. The last step is to add these together, canceling out any electrons that occur on opposite sides, which should be all of them if you balance them correctly in the second step. So when we add these together, those 6 electrons on the reactant side and the product side will cancel with each other. And then you'll just write what's left. And add back in the states of matter. It does not like me writing states of matter, apparently. And that was the half reaction method of balancing redox reaction. 3 steps. Now, the only thing I ever did to complicate this was sometimes I would put in a spectator ion. So instead of writing iron 2+ up here, instead I might have written it this way. I might have written it as iron chloride, like that. And on the other side, I wouldn't tell you what the products are. You would have to figure out what the products are. So that chlorine would go from the iron to the aluminum in the reaction. And chlorine itself would be a spectator ion. If you were to write the net ionic reaction of that, the chlorine ions would have canceled out because it would have changed or anything. It wouldn't have changed its charge. It wouldn't have changed its oxidation number. It's just a spectator. So that was as complicated as it got back in chapter 4. Ready for the new redox reactions? Any questions about the old method? Okay. Moving on to balancing new redox reactions here. So in a redox reaction where you're not actually seeing the charges, the way we determine what was being oxidized or reduced was by signing that oxidation number. And the oxidation number is basically, if it was ionic, what would be the charge on each atom in that molecule. So even though some of these things are ionic, not everything is. An element by itself with no charge always has an oxidation number of 0. The sum of the oxidation numbers has to add up to the oxidation state on the molecule. So the overall charge, if it's no charge, it has to add up to 0. If it's a polyatomic ion, it has to add up to the charge in that polyatomic ion. If you have something that is an ion, it's just the charge of the ion. For example, here we have potassium chlorate. Potassium, this is technically an ionic compound. If we were to write it as the two separate ions here, we would have potassium plus and chlorate minus is a polyatomic ion. So potassium plus, that means it has an oxidation state of +1. Now the chlorate ion, if I were to assign the oxidation numbers in chlorate, ClO3. Back in chapter 3 or 4, when we were learning how to assign oxidation states, there was a table of what elements take priority. For example, the most common oxidation state of chlorine is -1. But the most common oxidation state of oxygen is -2, and oxygen's oxidation state rule took precedent over chlorine. So we would assign it its oxidation state first and say, okay, oxygen is -2. I have to add up to this oxidation state or charge on the overall molecule. This is a polyatomic ion with a -1 charge here. So if I assign oxidation states to chlorine, chlorine can't be -1 because that's not going to add up to -1 overall. I have 3 oxygens that are -2 apiece, so that means it contributed what total towards the charge? Minus what? 6. So something plus -6 has to add up to -1 because that's the charge on our molecule. So what plus -6 gives me -1? 5. So that means our mystery number here for chlorine must be +5. So that's where that +5 came from. So that was the assigning oxidation states we did back in chapter 4. Now, when we look at it in terms of the reaction, we're not seeing charges change, but we are seeing the oxidation numbers change. Now, potassium starts as +1, and in the end, it's still +1. So if it didn't change at all, what do we call that ion? I just used the term. Good, spectator ion. So potassium is a spectator ion because its oxidation state did not change. Chlorine went from +5 to -1. Is that gaining electrons or losing them? Gaining. So chlorine was reduced. Well, what got oxidized? Oxygen. Oxygen went from -2 to 0. That is losing electrons, so that is going to be our oxidation. So in this reaction, chlorine was reduced and oxygen was oxidized.
Where did you get the -6 from that?
I have 3 oxygens. Each of them are -2, so that's a total of -6. If you were to draw this molecule, let's just not worrying about whether or not they're single or double or triple. Each of these are -2, -2, -2, so chlorine must be +5 so that overall it adds up to -1. Yeah. Not to be confused with formal charge. That was something different we did later. All right. So as long as the oxidation state is changing, you were a redox reaction, which means some very common reactions we have seen, such as the second one here is methane plus oxygen makes carbon dioxide and water. What kind of reaction is that? When something reacts with oxygen to make carbon dioxide and water, something containing carbon and hydrogen. That's a what reaction? Burning. That's a combustion reaction. So combustion reactions are also redox reactions because you can see the oxidation states of both carbon and oxygen change in this reaction. All right, so let's consider this reaction. I have iron reacting with the dichromate ion. Iron reacting with the dichromate ion. And the products are iron 3+ and chromate 3+. So as first blush, it just looks like a normal redox reaction, except for what on earth happened to the oxygens, right? And compared to the last one we didn't have anything that wasn't technically a spectator in there. We can't call oxygen a spectator ion because it is part of the polyatomic ion here. So it's going to take a few more steps to figure out how to balance this thing, because clearly it's not balanced. Now, some things to consider. whenever you have a metal that is an ion, we always wrote its state of matter as aqueous. So these reactions are always going to take place in aqueous medium, which means that we've always got plenty of what molecules floating around? Water molecules. So we can use water molecules to balance this, which is great because water molecules contain oxygen, and I see a big issue right here in that oxygen is in the reactant side, but there's no oxygen on the product side. So that's great. Another thing is most of these redox reactions take place in acidic solution. So in acidic solution, what ion do we have plenty of? Acids are things that release what in solution? Hydronium. Without the H2O, though, that's just the H plus, hydrogen ion. Remember, in aqueous solution, hydrogen ion and hydronium are equivalent because it's just with or without the oxygen. So we can also add plenty of hydrogen ion to this reaction, which is great because if we're going to be adding waters, that's going to throw in a bunch of hydrogens in there, so we can add hydrogen ion to balance it out. So these are the ideas behind how we can balance out this reaction. So unlike back in chapter 4 where there were 3 steps, there's going to be a few more steps. We're on page 878, and there are 7 steps to balancing a redox reaction in acidic solution. 2 extras, so a total of 9 if it's a basic solution. So step 1 is still the same. Break it apart into the 2 half reactions. Determine what was oxidized and what was reduced. So in that reaction, if I look at the charges here, iron went from 2 plus down to, or up to 3 plus. So that's clearly losing an electron. So that's oxidized. So even though you're not quite sure what's going on with this dichromate thing, iron was clearly oxidized, which means the dichromate must have been reduced. Now, honestly, in this reaction, or in this method, even if you're not 100% sure what is the oxidation, what is the reduction, we will figure it out later. So even if you could just break it into 2 halves and go, okay, something was oxidized, something was reduced, I don't know what they are, I just know these are the 2 halves of the reaction, and we will figure it out later. So don't panic too much in that very first step and get stuck. So, oxidation and reduction half reactions. That's step 1. Step 2 is we want to balance anything that is not oxygen or hydrogen, because oxygen and hydrogen we can balance later with adding water molecules and hydrogen ions. So anything that is not hydrogen or oxygen gets balanced. For example, in this reaction, iron is already balanced, but chromium is not. I started with 2 chromiums, and I only ended with 1. So I'm going to put a coefficient of 2 in front of the chromium in order to balance out that chromium. So that's step 2, balance anything other than oxygens or hydrogens. Step 3, now we're going to balance the oxygens by adding waters. So the oxidation reaction didn't have any oxygen in it, so we're just going to leave him alone for now. But the dichromate there has 7 oxygens. So if I have 7 oxygens on the reactant side, I need to show that there's 7 oxygens on the product side. So I'm going to add 7 waters to provide those 7 oxygens. And now the oxygens are balanced. But what did I mess up balancing-wise? Not mess up, but hydrogen. Now hydrogen's not balanced. Now how many hydrogens do I have on the product side? 14. So what do you think step 4 is going to be? To add 14 hydrogens. Remember, this is an acidic solution, so there's plenty of hydrogen ion flowing around. So step 4 is going to be balance the hydrogen by adding hydrogen ions to the opposite side of wherever you added water. So wherever you added water, now you have to add hydrogens to the opposite side to balance them out. Hydrogen plus ions. So that's step 4. So step 1 is to break them apart. Step 2, balance anything other than oxygen or hydrogen. Step 3, balance the oxygens by adding waters. Step 4, balance the hydrogens by adding hydrogen ions. So at this point, the atoms all look balanced. So we are technically where we were at the end of the first step in the last problem. All of our atoms are balanced. But what is still not balanced here? What was not balanced? Charge. Good, charge. Our electrons are not balanced. Now the problem is, the way we've written these half reactions, we don't actually see the electrons, so it's hard to figure out how to balance them. So step 5 is going to be showing those electrons. So how do you determine how many electrons to show? You do it by balancing out the charges. Now, in that first reaction, the oxidation is pretty obvious because iron 2 plus down to iron 3 plus means it must have lost 1 electron. A little bit trickier when we have more things going on here. So what we're going to do is we're going to add up the total charge we've got. So before, let me step back one so we can look at this before we've messed up anything here. If we add up the total charge on our reactant side here, I have 14 positive charges and 2 negatives. So overall, what's the total charge on our reactant side? 12, positive or negative? Positive. So 12 positive is my charge on my reactant side. On my product side, water has no charge, but chromium does. So what's my total charge on my product side? There's 2 here. 6 plus, good. 6 plus, because I have 2 chromiums and they're each 3 plus. So the charges are not balanced. What's the charge on an electron, positive or negative? Negative. So I need to take this 12 plus and make it 6 plus, which means I need to subtract it. I need to bring it down by 6 charge units. So to bring it down by 6 charge units, I need to add 6 electrons. So this portion again was going to be 12 plus, I add in those 6 electrons, so those 6 minus, and that brings me down to 6 plus. So 6 minus plus 12 plus is where this plus 6 comes with, so now it equals the charge on our other side. So yeah, technically now we're where we're at the end of the first step of the last problem. Don't worry, just 2 steps to go. 2 steps, and now we are at, since we were at the end of the first step of the last method, and the last method only took 3 steps, the 2 last steps are going to be the same for both methods. So looking at these, do the electrons balance between the 2 different reactions? Do I have the same number of electrons in my oxidation that I do in my reduction? No. Is that a problem? Yes. So step 6 is going to be the same as step 2 was in the last time, balance the number of electrons. So what can I multiply by that first reaction by to balance the electrons? 6. Good. So if I take that first reaction and I multiply by 6, that will balance so I have the same number of electrons in both reactions. So step 6 is to balance the electrons by multiplying the half reactions by whatever coefficient gets them to their least common multiple. So that's step 6. One more step to go. What was the last step? Combine them. Put them all back together. And what cancels out when we do that? The electrons. So there goes the 6 electrons and 6 electrons when we add them back together. And here is our balanced redox reaction. You should be completely balanced as far as the number of every atom goes. So 6 irons, 6 irons. 14 hydrogens, 14 hydrogens. 2 chromiums, 2 chromiums. 7 oxygens, 7 oxygens. You should all be completely balanced as far as the charges go. So we won't add them out, but trust me, the charge will balance out as well. And that's how you know that a redox reaction is fully charged. Both the atoms and the charges on both sides balance out. All right. Did you try this out? All right. I'm going to start a blank page. Sure. Here. And we'll do the sample problem. All right. Let's see here. Oh, real quick. If the solution is in a basic solution, I said that there were 2 extra steps you'd have to do to bring your total up to 9 steps. Because at the end of this, I've got all these hydrogen ions, which means I'm in an acidic solution. But what if I'm not in a acidic solution? What if I'm basic solution? Basic solution isn't full of hydrogen ions, it's full of what ions? Hydroxide ions. So if you are in basic solution, the first 7 steps will still be the same, but then you're going to have 2 extra steps, and here's the 2 extra steps. If you are in a base solution, you need to cancel out those hydrogen ions by adding hydroxide ions. Now here's the thing. When you are a half reaction, you can add whatever you want to balance anything to any side. But once you are a full reaction, the laws of algebra come back into play, which means if you do anything to one side, you must do to the other. So at the end of step 7, because I've added these back together, I'm a full equation. So if I add hydroxide ions to one side, I must add the exact same number of hydroxide ions to the other side. Good. So step 8 is for every hydrogen ion in the reaction, you're going to add a hydroxide ion to cancel it, and you must add the same number of hydroxide ions to the other side. So if this reaction that we just balanced was a base, instead, how many hydroxide ions would I need to add to both sides? 14. So I would add 14 hydroxide ions to both sides. Now, what do you get when you add hydrogen ion to hydroxide ion? What does that add up to? Water. So how many waters did I just produce on my reactant side? 14 waters. So I now have 14 waters. Is this reaction still balanced or something going on wrong? Does anything cancel now? Seven of the waters, right? I've got 7 waters over here on the product side, and I've got 14 waters over here on the reactant side. So the very last step, step 9, is to cancel out any extra waters. So these 7 waters would cancel, and this would go down to just 7 waters on the reactant side. So those are the last 2 steps, only if you're in a basic solution. And it would say right there in the question, you're in a acidic solution or you're in basic solution. I like to write out the number of steps off to the side and can't cross them out as I do them to make sure that I don't leave one out or do them out of order. So as soon as I read that question, I see the word acidic or basic, I write either 7 for acidic or 9 if it's basic, 1 through 9, and then I cross them out as I go through them just to keep track and make sure I do them in order. Because you can imagine, if you do any of these out of order, it will not work. All right, so let's try this out. Permanganate ion, MnO4 negative, and iodide ion, I minus, react in basic solution to produce manganese oxide and molecular iodine. Use the half reaction method to balance this equation. Now, to determine what was oxidized and what was reduced, a little bit trickier here because iodine is, well, you can kind of tell, but it looks like at first both things start out negative and both things start off with no charge. So to really determine what was oxidized and what was reduced, you can assign oxidation numbers. That's what they've done here. They've assigned oxidation numbers to everything. So looking at these oxidation numbers, the oxidized species was the one that lost electrons and therefore its charge went up. So what was oxidized? What lost electrons? Iodide. Good. Iodide went from -1 to 0, so that is losing electrons. What was reduced? Meaning its charge went down, or its oxidation number went down. Manganese. Good. Manganese went from +7 down to +4, so that's a reduction. And oxygen in most of these reactions is going to technically be a spectator. It won't be a spectator ion because it's not an ion. It'll just be a spectator because usually its oxidation state does not change. All right. So when we write our half reactions here, I going to I2 is going to be our oxidation, and the permanganate ion going down to the manganese oxide is going to be our reduction. So let's go ahead and write those half reactions over here. And we're also told that we are in basic solution, so it's going to take 9 steps. Go back to where I had space. So I'm going to write off to the side. I'll do it over here. 1 through 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can cross them off as we get them done. So step 1 was to write those 2 half reactions. So the oxidation half reaction is going to be the I minus going to I2. I need to rearrange this. I minus going to I2. And then the reduction is going to be that permanganate ion. The MnO4 minus going to MnO2. We don't really worry about states of matter with this. We've got enough going on as it is. So that was technically step 1, right? The 2 half reactions, so I'm going to cross out the number 1. What is step 2? Balance what? Anything except for what 2 elements? Hydrogen and oxygen. So is anything other than hydrogen and oxygen not balanced? Yes, iodide. So we need to put in what coefficient where? A 2. Put in a 2 right there. Let me. A 2 right there. Now is everything else balanced? Yes, so step 2 done. Cross it out. What's step 3? Balance your oxygen. So oxygen is clearly not balanced in that reduction. I start with 4 oxygens, I end with 2. So which side do I need to add waters to, and how many do I need to add? Good. If I add 2 waters to the product side, now I've just added 2 more oxygens. Added 2 more oxygens for a total of 4 oxygens on both sides. So step 3 done. How about step 4? Now my oxygens are balanced. What still needs to be balanced? Hydrogens. Okay. So hydrogens are definitely not balanced right now. I'm going to erase this word redox so that I can have a little more space here. Reduction. How many hydrogen ions do I need to add, and to what side? Good. 4 to the reactant side because I have 4 from that water. So 4 hydrogen ions to the reactant side. So that's step 4. Cross it out. So step 5 is the tricky one. This is where you balance out the charges. So let's look at these charges. Let's look first at our oxidation. Our oxidation reaction here, I've got what total charge on my reactant side? 2 minus. I've got I minus, and I've got 2 of them, so that's total 2 minus. What is my total charge on my product side? 0. This would be a minus, not an E. 2 minus. And that's 0. That's clearly not balanced. If I add electrons, they add negative charge. So which side should I add electrons to? The product side. Now this is an oxidation. So in an oxidation, you're losing electrons. So does it make sense that electrons would be a product? Yes. How many electrons am I going to lose here? 2. Because if I lose 2 electrons, now my product side is not a charge of 0. It's a charge of 2 minus. Okay. Now let's try and do the same thing, or try. We will do. There is no try, only do. To the reduction reaction. So I've got 4 positives and a negative for a total of what charge on my reactant side here? 3 plus. What's my total charge on my product side? 0. So which side do I need to add electrons to? The left. How many do I need to add? 3. Move this thing again. 3 electrons. Now again, this is a reduction, so it's gaining electrons. So we would expect the electrons to be written as a reactant. You should end up with the oxidation reaction, half reaction with electrons on the product side, the reduction reaction with electrons on the reactant side. If you don't, they can't cancel. So make sure you end up with both of them needing to add electrons and on two opposite sides, because that's how a redox reaction works. So there's step 5, cross it out. We'll go back to black. Step 6 now. What do we do next? Good, balance the electrons. So I've got 2 electrons in my oxidation and 3 in my reduction. So what am I going to multiply my oxidation by? 3. In my reduction, I will multiply by 2. I'm going to rewrite that down here. Distributing the 3, I have now 6 I minus. Goes to 3 I2s and 6 electrons. There's my oxidation reaction. Distributing the 2, I now have 6 electrons. 2 times 4 is 8 hydrogens, 2 permanganates, and 2 manganese oxides. And then 2 times 2 is 4 waters. Double check I did everything right. Oh. So that's step 6. 3 more to go. So what is step 7? Combine them. Good. So we're going to take these reactions, we're going to add them. When we do that, what will cancel? Good. Those 6 electrons will cancel, and then we'll just write everything else. And a lot of students ask me, does it matter what order you write it in? Honestly, it does not. It doesn't matter as long as you keep track of what's a reactant, what's a product. But I usually like to write the hydrogens on the far end, especially in a reaction like this, which is basic because that's what we're going to have to get rid of in a second. So I'm going to write the 8 hydrogens plus 6 I minus plus 2 permanganate. And there was your step 7. Two more to go. Because we are in a basic solution, we've got these extra steps that we only have in basic solution. What was step 8 if you're in a basic solution? Good. Good. Add hydroxides to cancel out the hydrogen ions. So I have 8 hydrogen ions. So how many hydroxides I'm going to add over here? 8 hydroxides. Because I'm now a full equation, anything I do onto one side I must do to the other. So I'm going to also add 8 hydroxides over here. Now, these 8 hydrogens and 8 hydroxides on the product or reactant side are going to add up to make 8 waters. So what is going to be step number 9? Cancel out extra waters made. So how many waters are going to cancel? 4. I've got 4 on my product side, so this number 8 is going to go down to 4. So now I have 4 waters, and then I'll write everything else, plus 6 I minus, plus 2 permanganates, goes to 3 I minus, plus, you're right, that should be I2. 2, and I'm left with 8 hydroxides. And there's your final finished answer. Whew. Now to save space, since I had limited space on the slides here, I kind of did multiple steps on the same lines instead of rewriting the equation each time. If you look on page 880 where it shows this equation fully worked out, it breaks it down and shows you what the equation looks like at the end of each step, which is helpful when you're learning how to do it. It's also helpful if you do it that way on your test, because if you don't get the final answer right, and I'm going to try and figure out where things went wrong and how much partial credit you deserve, it's easier if I can tell which step something went wrong on. But to make it all fit on one paper, that's why I did it this way instead of rewriting it each time.
Yeah.
So step 1, step 2, step 3, step 4, step 5, step 6, step 7, step 8, and then step 9. Any questions about that?